Start.
Good afternoon, friends. Today, the third module of this course on neutron scattering is beginning. This is on neutron inelastic scattering, a very special quality of neutron scattering, a property or technique which is not available by any other radiations like X-rays and electrons. So this module will be taken by Professor S.L. Chaplot, an expert in the field, and he has been working in this field for a long time and a renowned figure not only in the country but abroad. So now, without any further ado, I'll request Professor Chaplot. हेलो
बंद किया क्या? स्टार्ट करें? हाँ, you can start. थोड़ा माइक से थोड़ा नजदीक रहिए. You have to go close to the mic.
This
Not
one?
that one. That one. That one. That's what is this one? This mic. What is it? Yeah.
Okay, good afternoon, everyone. Thank you, Dr. Saibal Basu, for the introduction and for coordinating this nice course. We have already covered the basic principles of neutron scattering and also the neutron diffraction over the last 2 months. And now we are going to talk about the third module, that is neutron inelastic scattering or inelastic neutron scattering. As you can see from this projection, this will cover essentially two aspects, the so-called inelastic neutron scattering and the quasi-elastic neutron scattering. In the next few projections, we will learn about this. The essential difference is that inelastic neutron scattering, we study the various kinds of periodic dynamics. And with quasi-elastic neutron scattering, we study not the periodic dynamics, but stochastic dynamics. Okay, I have been at the Bhabha Atomic Research Center for last 4 decades. These are some of my colleagues, Mayank Gupta, Dr. Mishra, Prabhata Shri Goyal, Ranjan Mittal, Mala Rao, Virendra Sharma, Subhankar Mutra, and Ramaprasad Mukhopadhyay. These are my colleagues during the last few years. I have learned a lot from by interacting with these colleagues, and so I would like to thank them. Now, okay, the next one should come from the keyboard, right? Oh, okay, it's...
yeah, correct.
Okay, good. Okay, I can use this one, yes.
This is a...
Yeah, fine. Okay, so what are we going to cover in the next 10 or 12 lectures? Will be use of these techniques to study things like phonon dispersion curves or phonon density of states, magnetic excitation. So these are all excitations which are essentially periodic in nature. So that is the inelastic neutron scattering. Okay, I may just add that if you want to look at specific excitations at a specific wave vector or specific energy, that is certain point in the phonon dispersion relation, then you need a single crystal, because you can define a vector, a wave vector, only when you have a single crystal. With a powder or polycrystalline sample, the direction gets averaged, and you get some average properties like the density of states. We will also discuss translational and rotational diffusion. Well, diffusion, diffusion is in a very general sense. What I really mean is stochastic dynamics. As you know, the diffusion in a solid is very different from diffusion in a liquid or in a gas. In a solid, because of the underlying solid structure, the diffusion is accordingly modulated. At short range, this might involve atomic jumps and so on and so forth. So there are a variety of diffusion motions. It could be molecular translation, molecular rotation, reorientations, and a variety of other things. Now, the data analysis of these complex dynamical phenomena has to be done through corresponding theoretical tools. So, for example, for phonons, we have the well-known and standard technique of lattice dynamics. And for stochastic dynamics, the molecular dynamic simulation can be used. So these are really required for whenever you have a complex dynamics. Okay, anyway, this is just an outline of the kind of things we would like to cover. So let's move on. Okay, so what does it involve? Inelastic scattering, or see, neutron scattering in general, you have a neutron beam incident on a sample, and you study the neutron beam which is scattered from the sample. Okay, so the beam can be incident. This beam, well, as you would have already studied in the basics, either from a nuclear reactor or a spallation neutron source by any other means, you essentially require a monochromatic beam of neutrons with a definite energy, a definite wave vector, or a wavelength. And we are also interested in its polarization state. So the spin state, whether it's spin up or down with respect to a magnetic field. So now once I have these characteristics of an incident beam, and the neutrons fall onto a sample and then they're scattered, one would like to study the scattering in all possible directions. So essentially in a 4 pi solid angle. So okay, but in a given plane, if you have the angle between the outgoing beam and the incident beam, that we normally know is like the 2 theta, that is the twice of the Bragg angle in case of diffraction. Now, so the outgoing beam, we again have these numbers, the final energy, the final wave vector, and the final polarization state. Okay, so these are the symbols we are going to use. They are EA and EF, these are incident and scattered neutron energies. KI and KF are incident and scattered neutron wave vectors. What I mean by wave vector is essentially a vector in the direction of the neutron beam, and the magnitude of the wave vector is 2 pi by lambda, lambda being the wavelength. And PI and PF are the incident and scattered neutron polarization. As you know, neutrons have the spin. And the polarization analysis is particularly relevant for magnetic scattering or the magnetic structure. Now, just to look at the numbers, so the wave vector magnitude is 2 pi by lambda. The energy of the neutron can be written in terms of the wavelength by this equation. This you can verify by the standard momentum square divided by 2 or twice the mass. And just to appreciate the numbers, if the energy is in milli-electron volt and the wavelength in angstrom, then we have this numerical relation that E is about 80 divided by lambda square. So typically for thermal neutrons, the wavelength is in the range of the order of an angstrom, And so the energy for a 1 angstrom neutrons would be 81.8 millielectron volts. Okay, if the energy is 25 millielectron volt as the thermal energy at room temperature, then the corresponding lambda is about 1.8 angstroms. So these numbers you would have already, I'm sure in the previous two modules you would have learned, it just to remind ourselves. So okay, so that is the basic principle of that we need to be concerned with. And what you have in case of diffraction is something very simple. See, diffraction essentially combines the elastic and inelastic scattering, and that is because we don't do any energy analysis of the scattered neutron. So if you don't do any energy analysis of the scattered neutron, and okay, largely the scattering is elastic. Okay, it so happens that it is largely elastic at low temperatures, thanks to the Debye-Waller factor and various things like this. So in case of diffraction, one just assumes kf equal to ki, that is the energy of the final neutron, energy of the incident neutron, that are assumed to be equal. And then you can write these vector relations, vector ki minus kf equal to q, that is the wave vector transfer. Okay, so this is just a revision of your diffraction class. You have a vector difference ki minus kf equal to q, that is a wave vector transfer. And you can work it out that if 2 theta is a Bragg angle, 2 theta is the angle between the incident and outgoing beam, then the magnitude of this wave vector can be written as 4 pi sine theta by lambda. Okay, this I'm sure you can work out. Okay, and then the famous Bragg condition is nothing but that this wave vector transfer is equal to a reciprocal lattice vector with some indices HKL. So if you have a reciprocal lattice vector G of HKL, and the Bragg condition is that that has to be identical to the wave vector transfer, then only you get the Bragg condition is satisfied. And so you just see the magnitude of G is nothing but 2 pi by d, d being the lattice spacing. And so if I equate these two, I just easily get the famous Bragg condition, 2d sine theta equal to lambda. So this is what one essentially does in neutron diffraction, or X-ray diffraction for that matter. And then this is the basis of all the crystallography, whether with a single crystal or with a powder sample. However, just to remind you, there is also a lot of scattering away from the Bragg condition. So it is not that the scattering occurs only at the Bragg condition. At the Bragg condition, it is very large because there is a very constructive interference because of the periodic structure. But however, one has a lot of scattering, the so-called small angle scattering, or what one measures in reflectometry. This is at a very low theta, very small angle, much below where you get the Bragg reflection, and that is normally referred to as low Q scattering. And this has different kind of information, not the crystallographic information, but information about any large scattering entities in the sample, macromolecules, or in any other structures, not at the unit cell level, but something at the order of 100 angstrom or 1000 angstrom. Reflectometry again deals with the surfaces. In addition to this, there are also techniques in diffraction known as the total scattering, which goes up to small q to large q. And this has the Bragg scattering as well as scattering due to any disorder in the structure or the amorphous nature or liquid or so on. So when one has the total scattering, then one can use standard techniques of Fourier transform or Monte Carlo and so on to get the structures. Well, we are not going to talk much more about this. This is just to let you know, this is just a revision of the diffraction, so to say. And and the fact that you have the break scattering as well as the total scattering at all Q values. Okay, if any of you think that I'm going too fast, we can slow down. But I suppose so far it has been just a revision, so it should have been okay. Now we come to inelastic scattering. So in this inelastic scattering or quasi-elastic scattering, the essential difference compared to diffraction is that we do energy analysis of the scattered neutron beam. Okay, so the neutron beam which is scattered at various angles in a 4 pi solid angle around the sample, we measure the intensity as a function of the orientation, as a function of the direction, as well as we also do the energy analysis. So that means we also measure the spectrum of the energies, neutrons, a spectrum of the neutron energies that are scattered from the sample. So there's you can essentially say it's a 4-dimensional information. The 3 dimensions of the angle, the solid angle, and the 4th dimension is the energy. In diffraction, you are looking at only the 3 dimension of the solid angle. So here, this is the 4th one. And so now once you do the energy analysis, you not only you don't assume that Ki and Kf or the energy Ei and Ef are equal, but you look at the energy difference. So this difference can be also represented as h cross omega, omega being an angular frequency. Here I'm not implying that it is an excitation or anything. It is just writing energy in terms of h cross omega. Okay, just leave it there right now. And Ki minus Kf is the wave vector transfer. So now here E is the energy transfer associated with the scattering process, and Q is a wave vector transfer associated with the scattering process. So these are again the basic notations, and they apply to all kinds of inelastic or quasi-elastic neutron scattering, including magnetic scattering. In case of magnetism, we also have the spin neutron polarization before and after the sample, and that we will come right. We will not discuss those things at every step, but again come back to it when we discuss the magnetic inelastic scattering. Okay. Now, so just to get an overview of what we look at and what is done by other techniques. So of course, as we said, the structure is widely studied by X-ray and neutron diffraction. So this is well known, and I assume that you already know about it. As far as the dynamics is concerned, yes, we talked about neutron inelastic and quasi-elastic scattering. But the techniques which are much more widely used are the Raman scattering, Brillouin scattering, infrared absorption. The only major limitation that these techniques have, they are very, very popular because they use very intense source of incoming radiation, lasers in particular. And because of such an intense source, these experiments are very efficient compared to neutron scattering, because neutron scattering, the neutron beams are not very intense compared to the laser beams or photon beams which you use. But here the major limitation is that the wavelength of the incoming radiation here is typically of the order of 5,000 angstroms. So when that is the wavelength you have, the corresponding wave vector transfer, which is like of the order of or 2 pi by lambda, is 0.001 angstrom inverse. So you can see that this number is extremely small compared to the size of a Brillouin zone. So which means we are close to the Brillouin zone center. So all kinds of dynamics that can occur at a very long wavelength of 5,000 angstrom or at a wave vector which is close to the Brillouin zone center, it is much more efficient to study using the optical techniques. Of course, there are some selection rules, issues. Not all kinds of excitations are Raman active or can be observed in infrared absorption. Besides that, these are the sought after or the technique of choice. Neutron scattering, as I said, is much less efficient, but it allows for all wavelengths which are of interest in a solid material. So right now, what it means is that you don't worry about very large wavelength, but of the order of 1 angstrom or a few angstrom. So less than 1 angstrom to maybe about 10 angstrom, that kind of things can be easily done. And that will cover the entire Brillouin zone, which means all the excitations that we can talk about in a solid, in a periodic solid. And even if it's not a periodic solid, then of course we don't have to worry about the wave vector in particular. So you can still study them. And again, the stochastic dynamics, which involves small wavelengths or the disturbances at a very small distance of a few angstrom, like diffusion from atomic site to site. These kind of things can be studied using neutrons because the wavelength matches the corresponding distance involved in these dynamics. X-ray inelastic scattering is again getting very popular. However, these are the main limitation here is that because the X-ray energies are in the range of kilo-electron volts, not milli-electron volts, but kilo-electron volts, and therefore to study excitations which are in the range of milli-electron volts, you need from kilo to milli, that means about you need an extremely high energy resolution of delta E by E of like 1 in 10 million. And so such high resolution again reduces your beam intensities and requires a high degree of monochromatization and also the analysis of the scattered beam. So these are possible at the fourth generation synchrotrons, and again a very powerful tool. And again, this has the same advantages as the neutron scattering has, like all kinds of wavelengths of periodic dynamics. However, this has limitations of studying stochastic dynamics because, as we will see, these require even smaller energies quite often, and that may or may not be possible to probe even with excellent resolutions like this. Okay. So let's come back to neutron scattering. Here, as I said, we probe the scattered neutron beam in 4 dimensions, the 3 dimensions of space and the 4th dimension of energy. And so one defines what is called a scattering cross-section as a function of these 4 dimensional variables. So, okay, formally one can say it is the probability that an incident neutron is scattered by the sample into a solid angle d omega around omega with energy transfer dE around E. And okay, this can be numerically written in terms of per unit solid angle, per unit energy transfer, per unit incident flux, and so on. So this kind of quantity, we don't always need to kind of put it in absolute scale, but this is the formal definition. And this scattering cross-section is, as you will see, is simply proportional to the so-called dynamical structure factor. Now, dynamical structure factor is just, again, a 4-dimensional quantity of, which is just a way of writing this probability in terms of the 4 dimensions of space and the wave in the reciprocal space of the wave vector and the angular frequency. Instead of energy, we use angular frequency for the reasons I will just explain in a moment. But so there is a dynamical structure factor, and this quantity essentially has information about the dynamical structure. Unlike the static structure, where you talk of only S of Q, not about omega, because you don't do energy analysis of the beam. So you integrate over all possible energy changes, and that has information. The static structure factor has information about the structure. That means how the atoms are arranged in the solid, whether crystalline or amorphous or whatever it is. So that's static structure factor. We also have a similarly dynamical structure factor, which is the extension in the fourth dimension. Okay. Now, all right, so let us see what we have already discussed so far. So the incident energy is final energy plus h cross omega. Is in fact, this can also be seen as a statement of energy conservation. Similarly, if I write Ki equal to Kf plus Q and multiply by h cross, then this is the momentum of the incident neutron, momentum of the scattered neutron, and this is the momentum transfer. So it's again, this can be seen as a statement of momentum transfer conservation. In fact, you have the same kind of equations also for Raman scattering, where you have talk of energy conservation and momentum conservation. So the basic principle is the same, whether you have Raman scattering or neutron scattering or inelastic X-ray scattering. And this scattering cross-section, as we just said, is directly proportional to the dynamical structure factor. Now, this dynamical structure factor, if particularly not for the magnetic part, but for the nuclear neutron scattering, as you already know, neutrons principally scatter from nuclei besides the magnetism of the orbital electrons. So the nuclear part, the Fourier transform of this quantity is essentially a position-time correlation function. Okay, this you can simply, it's a four-dimensional space, and so the corresponding four-dimensional space from the reciprocal to real space is R and T. And so the correlation between the atoms in space and time is so-called position-time correlation function. When you have only the diffraction, when you look at only the diffraction, not the omega and T, then the G of R is like the pair distribution function of the vector distances between atoms, and the Fourier transform gives you S of Q, and here this is the position time correlation function. Now this quantity, now these are here, as we already said, if omega may be distinct frequencies, so if they're distinct frequencies, then these are of vibrational frequencies, whether these are phonons or any molecular vibrations, then this, as we said, is called the inelastic neutron scattering. On the other hand, if the correlations, the time correlation is stochastic in nature, say something like a function that may decay like an exponential function, a stochastic decay function with a certain time constant, then its Fourier transform, as you know, is a Lorentzian function. And so you may have a scattering which is a Lorentzian spectrum centered at the zero energy or zero frequency, and that is called the quasi-elastic scattering. So that is how, when you have delta functions in omega or the energy transfer, like Raman scattering, you see the peaks at distinct quantized energy changes, then these are inelastic scattering, and if it is around the zero energy transfer in a Lorentzian-like shape. These are not strictly always a single Lorentzian. This is just a simple way of putting it. In fact, in practice, we have, depending on the nature of the stochastic dynamics, you may have a fairly complex relaxation function, and the corresponding Fourier transforms may be quite complex. So this is all that one has to kind of have a proper model or do a proper theory and so on and so forth. But it all comes under the category of quasi-elastic scattering. And again, so also the vibrations, there can be a large number of vibrational frequencies or excitations, and then they will give all distinct energy changes like in Raman scattering. So of course, as I just said, in case of diffraction, you don't worry about omega. So it's just an integration over all omegas. Fine. So let's move on. How does it look like? So as we have already discussed, neutrons, thermal neutrons in particular, we have to be very careful. We are talking of thermal neutrons. not fast neutrons or so on, which have energies in millions of electron volts. We are talking of thermal neutrons, which are, and why we call it thermal neutrons is because these are neutrons which have been in thermal equilibrium with some matter, okay, around ambient or little bit high or low temperatures. And so because of those, that thermal equilibrium, whether it's a thermal neutron reactor or even a spallation neutron source. See, in a spallation neutron source, you get energies which are in millions of electron volts, but then they have to be thermalized, going through some kind of a thermal equilibrium with the medium. And so you get then the energies which are of interest to in material science or in condensed matter, solids or liquids and so on. So, and then the corresponding wavelengths are in angstrom. So these are the energies you're talking about. And as I said already, these are these are the so-called thermal neutrons. And so what we just discussed, if I do if I just show a spectrum qualitatively, so this is what we have plotted here is the energy transfer. Okay, we have said energy, but okay, it is just omega, which is the angular frequency, and energy is h cross times the angular frequency, and that the center line is at omega equal to 0. You can have energy loss or energy gain in the sense that what I mean is that you can h cross this omega here. You can if EI is larger than EF, the incident energy is more than final energy, then that means the neutrons has lost energy. So that's energy loss. And energy loss, then we say that this excitation is kind of created. So neutron loses energy and it passes on that energy to some excitation. So that's a neutron energy loss spectroscopy. And it can be neutron energy gain also, in which case the neutron absorbs energy from a bath of excitations and gains in energy. So you can measure on both sides. There are, like in Raman scattering again, these are Stokes and empty Stokes sites, and there are some differences in intensity because of what we call the detailed balance. I'm sure in the basics you would have already learnt about it. So that will affect essentially the intensity between the loss and the gain side. As you know, the intensity is larger on neutron energy loss side. So this is a preferred because you get more intensity this side, and no matter what the temperature is, and on the gain side, it is the intensity is less. Okay, and as I said, these are okay. Here we have put some broadening because okay, just representative of the instrumental resolutions, but otherwise, like Raman scattering, from periodic dynamics, you essentially get delta functions in a large number of delta functions corresponding to the excitations, and that is the inelastic scattering. And from quasi-elastic scattering, from a relaxation kind of a stochastic dynamics, the Fourier transform is like a Lorentzian, and then so this spectrum is a quasi-elastic spectrum, and the width of this spectrum has information about the relaxation time constants and so on. We will come back to it. So in general, it will, and you will also have some elastic scattering, which is again coming from the structure. Okay, in general, you have elastic scattering, you have quasi-elastic scattering, and you have inelastic scattering, and the various intensities that are balanced by temperature in particular, because these intensities, inelastic scattering intensities build up with temperature, and and so on. Okay. So that is just again the way we define these quantities. Okay, now let's look at what are the energy scales we are talking about. See, already we said that the thermal neutron energies these are the energies we have, but why? Why do we look at these energies? So let us say what are the energy scales we are talking about. So now, as far as the excitations are concerned, you have, as I said, E equal to h cross omega. That's the formally we wrote it like this. And once you have excitation, then the omega is, this is the energy of the quantum of the excitation. It can also be written as h nu. So nu is a frequency, not the angular frequency, but frequency. And nu can be written as 1 by t. So there is a period of oscillation. Okay, presumably a simple harmonic oscillator. So then that is it. And okay, the typical quantity of interest, like the atomic displacement in a simple harmonic oscillator, is like cos omega t. So omega is the angular frequency, t is the time, and so on. Now in solids, we know that the typical frequencies are in the range of a terahertz, and so the total time period, corresponding time period, is a picosecond. So we're talking of time period of the order of a picosecond, frequency of terahertz, the angular frequency 2 pi terahertz, and the corresponding energy. If you convert this energy for a neutron, or no, not just for neutron, but if you put these values here, the omega, then multiply by h cross, then you get energy in the units of milli-electron volts, about 4 milli-electron volts. If you convert in centimeter inverse, that people more familiar with Raman scattering or using that convention, so these units will translate to 33 centimeter inverse. Okay, so that's the energy scale we are talking about, and that is why thermal neutrons are useful. Phonons typically occur in the range of 0 to 200 milli-electron volts. Again, the values are determined by the strength of the interatomic bonding. So, for example, in the van der Waals solids, which are relatively weak bonding between atoms, then the phonon energies are less than or around in this order of 10 milli-electron volts. If you have stronger bonding like ionic or covalent bonds, then, and particularly the bond stretching, then this bond stretching tends to be pretty strong, and so therefore the energies are, bond bending are here. Bond stretching goes up to even higher values. Okay, so once again, if it's a hydrogen-hydrogen or a carbon-hydrogen, a light atom, then the corresponding frequencies or energies are even higher. Lighter atoms will have a larger frequencies. And but this is again the energy scale we are talking about. Typical lattice modes in which are not limited by any covalent stretch or bond bending would be somewhere in this range. Okay, it could be tens of milli-electron volts. For example, a good example to cover here is just the graphite, because graphite has the van der Waals interaction between the layers of graphite, hexagonal layers of graphite. So then the modes which are polarized perpendicular to the graphene plane or the graphite plane tend to have these energies. The modes which involve stretching, carbon-carbon stretching modes are in this range, and the other bending modes are in this range, and so on. Okay, so these are about phonon excitations. Magnon excitations again have similar values, again depends on the strength of the magnetic interactions and so on. So typically they are in the same ballpark. Stochastic dynamics, which is easy to call it diffusion, although diffusion has a limited meaning. But what we here really mean is all kinds of stochastic relaxation processes. So let's say, so these, as we already said, these can have a Lorentzian kind of distribution, unlike the delta functions here. And so if you have a relaxation function which is exponential minus t by tau, tau being the relaxation time, then is the Fourier transform the angular frequency will be inverse of the relaxation time. Okay, so you can see there is a difference here. Here h cross omega was h by t, So whereas here H cross omega is H cross by T. So therefore, a relaxation time of 1 picosecond actually translates to the half width at half maximum of about 1 terahertz or 0.6 milli electron volts. So this is not a delta function, but the half width at half maximum, unlike here. So I mean, this conversion from the half width at half maximum in case of stochastic process is not same as conversion between the energy of an excitation and its corresponding time of oscillation. There is a factor of 2 pi in between. So just this you can work out. I mean, for example, it may be a good problem to look at that if you assume a U like this and you do a Fourier transform of this quantity, then what kind of Lorentzian function you get and what is the width of the Lorentzian function. Okay, so that you can verify essentially these numbers. If you can't do it, then we will see whether we can manage. Okay, so typically the atomic jumps in a solid, because as I said, diffusion may occur not like in a continuous process as in a gas or liquid or something. Where again, there also it is like a diffusion, but it's a different kind of, the details are different. But if you have typical atomic jumps, which jump times of the order of a few picoseconds, then the corresponding Lorentzian widths are in the range of are a fraction of milli electron volt. So these are fairly small values. In fact, some even slower relaxations are polymer relaxations, which go down not a picosecond but even a nanosecond, and then the corresponding energy changes are even smaller. So you can see that we are talking about a very broad range of energies, 100 milli electron volt down to a micro electron volt. So this is several orders of magnitude range. And so in fact, there are a variety of neutron spectrometers which cater to different ranges of ranges. It's very important that when you have an experiment, you have an idea of what kind of energy changes and wave vector transfer that your physical process involves, what you wish to probe. And depending on what you wish to probe, you must you need to select a suitable neutron spectrometer which will cater to that those values of the energy changes or wave vector transfer changes. You cannot go to just any inelastic scattering spectrometer and hope to look at this vast range of physics that one can look at. So therefore, there are a large, very broad variety of spectrometers at thermal reactor sources as well as at the spallation neutron sources. There are tens of spectrometers of this kind and which are relevant. Okay, so we just said, okay, what are these spectrometers like? We will try to come to this, talk about it today, maybe a little bit, or move over to it later. So the energy scales, as I said, are in this, for inelastic scattering is typically, well, it starts from zero because, acoustic modes, for example, start from zero. And so there can be very low energy modes as well. Quasi-elastic scattering in this from a micro electron volt to a milli electron volt. So as I said, there are a large number of spectrometers which involve different techniques and different instrumental parameters which are carefully chosen to meet different ranges. So okay, the most important one which which started way back in 1950s is the so-called triple axis spectrometer. This is something like you have a double monochromator or a triple monochromator in a Raman scattering. So you have an incident beam of Raman photon or laser photons, and you do the energy analysis. Here it is a triple axis spectrometer. We'll come back to it. So essentially this has a crystal monochromator and crystal analyzer, and depending on various combinations, you can meet this. There is also a specific so-called filter detector spectrometer where instead of a crystal analyzer, one uses a filter. Then the other major different technique is neutron time of flight technique. So instead of a crystal monochromator where you can determine the wavelength using a Bragg reflection, here in a time of flight machine, you measure the neutron time of flight. And once you know the neutron time of flight, you know the corresponding velocity of the neutron and the energy of the neutron, and you know the direction of the neutron already. So you can get the wave vector and energy. So these are two major different techniques, triple axis, that is a crystal spectrometer and the time of flight spectrometer. Okay, a crystal based and a time of flight based. Of course, there are mixed techniques in which you have a mixture of time of flight and a crystal. For example, you can have a time of flight on, see, there are two sides of a spectrometer, the incident side where you choose the incident energy, and the scattered side where you choose the scattered energy. So it is possible that one of them is a crystal, other is a time of flight. Okay, from various considerations of energy and Q ranges, one does that. Then there is a very special spectrometer called backscattering spectrometer. So this is actually a crystal analyzer, but a backscattering means the Bragg angle is close to 90 degrees. And if you have a Bragg angle which is close to 90 degrees, then this can provide a very high energy resolution. So this energy resolution can be of the order of a microelectron volt. Okay, so again, of course, you lose intensity, but you gain in neutron energies. And then there's a totally different technique called neutron spin echo spectrometer, where actually you use the neutron spin and the precision of this spin in a magnetic field, typically a few hundred Gauss. Okay, it's not a very large field, but it's a large field over a long, large space of the scattering region. And that can be used as a clock. And once again, this technique also gives energy resolution, which is in the range of a microelectron volt. So both of these techniques giving very high energy resolution of a microelectron volt, these would be, are used in largely for quasi-elastic scattering of very slow relaxation like polymers and so on. And also where you need to do an extremely high energy analysis, maybe for specific enharmonic phonons or and so on and so forth. So these are the broad techniques. Perhaps we stop here. I don't know. I mean, I think it's, I would, in the next lecture, let me just say what I plan to do. We have about 347. So, okay, let's check, get a preview of what we will do next time. So we'll come back to details as required, but just to see. So for example, this is some detailed schematic of a triple axis spectrometer. You have neutrons coming from a reactor. Okay, then from a crystal, you choose a particular Bragg plane, and the Bragg condition, so that the Bragg condition is satisfied, and so you can choose a monochromatic beam of neutrons of a particular wavelength. It falls onto a sample. Then again, the spectrometer has the possibility of all kinds of 4pi moment around the sample. So you go in a particular direction and again do the energy analysis using another crystal, a Bragg, look at the Bragg reflection and then measure. And then you have a neutron detector. Dr. Basu, this instrumentation was already covered by somebody? Very catchy. Okay, so we'll just go a little bit more. So this is, a schematic of a so-called triple axis spectrometer where there are 3 axes: the monochromator axis, the sample axis and the analyzer axis. Okay, where movements are possible, and such a spectrometer has a large number of motors, and okay, these are more details. Maybe we'll come back later. You have neutrons coming from a reactor, and then there's a large monochromator drum. There's a sample stage, and then therefore there's an analyzer stage, detector, and so on. And again, there are further techniques like you can do Ki minus Kf, that is a momentum transfer. You can plan it in such a way that you scatter at a fixed value of Q and do an energy analysis, or vice versa. You can do at a fixed value of energy transfer and do a momentum scan and so on. Okay, these are some pictures of the spectrometer and so on, what we can do. This is some development which is being done at Dhruva. We'll talk more about it next time. So these techniques are available at the Dhruva reactor in Trombay, both this inelastic scattering. Time of flight, as I said, has see you have a neutrons coming from a reactor side, but then you have to take the neutron time of flight over a fairly long distance. Okay, you can have the monochromatic beam similar to.
They are aware of time of flight, right?
That much they would know.
No, what is
Yes.
the time of flight?
Right. Even the numericals would have been done, no?
Numerical also.
Yeah. Okay, so this we'll come back to it next time. So you have these are again large machines running over several, or maybe 10 meters or longer, where you have the incident side and the scattered side, and you measure it. Again, some developments are there. Okay, so I think I will like to stop here today. And if there are any specific questions you'd like to ask now, okay, we'll be happy, and we'll continue. Whether you want me to go a little slower or faster, or essentially, I mean, this was an introductory talk. Next one also, we will talk about general aspects of neutron scattering. So that means the first two talks will be on general aspects of inelastic and quasi-elastic neutron scattering. And then we come to specifics of phonon dispersion curves, or quasi-elastic neutron scattering, or and so on and so forth. Dr. Basu, is there anything? Yeah.
No.
Okay, great. Yeah, you can send it by email, by whatever method you have been already told, and I'll be very happy to look at them. And if there are general interest things, we'll talk about it in the next lecture. Okay, so thank you very much. We close here.
आ जाइए काउंसिल हॉल में